Today we will discuss about Nash's conceptual model and how it can be utilized for flood routing. This tutorial is also available in the website boipatra.ws, and you are listening it as a podcast of Boipatra VSC newsletter. So Nash's conceptual model was proposed by J. Nash in the year of 1957, and it is actually a hydrologic model which can predict the instantaneous unit hydrograph of a watershed. It assumes that a watershed can be represented by a series of n identical linear reservoirs, outflow of which each of the reservoir is the inflow to the next. Okay, and each of the reservoir has K as the storage coefficient or storage constant, which is same for all the n number of reservoirs. And the final outflow can be derived from the nth reservoir, which represents the instantaneous unit hydrograph for the entire watershed. So the final outflow from the nth reservoir will give you the IUH of the entire watershed. So there are only three things that you must remember here. One is the gamma function. Second is the parameters of this equation, n and k. I have just now discussed what is n and what is k. And how you can find the flood hydrograph, or how you can route the flood hydrograph with the help of this equation. So key components is the gamma function. You can see this is the gamma function. K is the storage constant. T is the time. E to the power t by k, all are self-explanatory. Okay, so mainly the parameters are n, number of reservoirs, and storage constant k. So this model has been applied widely in rainfall runoff analysis, design of drainage system, etc. So numerical example, if you want, you see, if I want to calculate IUH for a watershed modeled with 3 reservoirs, n is equal to 3, and storage constant k is equal to 2 hours, then the IUH equation for the reservoir, this has been derived from the gamma function. So it will be t to the power n minus 1 e to the power minus t by k divided by k to the power n minus 1 factorial. Now as usual, t is the time in hours, n is the number of reservoirs, k is the storage constant, n minus 1 is a factorial of n minus 1. So here n and k is that n is the number of reservoir. In this problem it is 3. Storage constant k is 2. So just substitute the values accordingly to find the IUH at t. Now if I want to find IUH for t is equal to 4 hour, then what happens is, this is the way I have to do. Substitute values, n equal to 3, k equal to 2, calculate IUH for t is equal to 4 hours. Just put down the values and ultimately final unit will be 0.135 centimeter per hour. Okay, so this is the solution. Second is how Nash's conceptual model for IUH generation can be used for flood routing. Let us see. I'm not going to deeper about this. You can easily download this entire tutorial, and I will give the link in the description. So let us see an example. Problem statement, a watershed generates runoff due to a rainfall event. The IUH, instantaneous unit hydrograph for the watershed, is modeled using Nash's conceptual model with 3 reservoirs. That means n is equal to 3 and a storage constant of k is equal to 1 hour. Okay, the effective rainfall over the watershed lasts for 2 hours with an intensity of 5 millimeter per hour. So 2 hour is the effective rainfall, and intensity of that rainfall is 5 millimeter per hour. We want to route this rainfall downstream to compute the direct runoff hydrograph at the outlet using Nash's IUH. So this is the problem. So my main prediction or main objective is to predict the direct runoff hydrograph from this Nash's instantaneous unit hydrograph. What do you have to do? Very simple thing. This is the IUH equation. I have already discussed about this in my previous slide. This has been derived from the gamma function. Just substitute the values of n, k. So accordingly it will give. Now as you are drawing a hydrograph, so you need to have the discharge. This IUH at T means discharge from the unit hydrograph at the tth hour. So if you want to draw a hydrograph, you need the discharge at a regular interval or that at every time step. Now here we will use T is equal to 3 hours. So we have to first calculate the peak discharge with the help of the IUH formula for respective time at T is equal to 1 hour, T is equal to 2 hour, T is equal to 3 hour. So just put the value of T as 1, K as 1, N as 3, and you will get the value this. This is after 1 hour. Then when you put T is equal to 2, then you again put here T2 and N and K is same because N and K are not changing in any hour, any time scale. So T is equal to 2, so this is this. At T is equal to 3, this is this. Why T is equal to 3? Because that is our problem. Because this effective rainfall has lasted for 2 hours. So if it is lasted for 2 hours, then you can understand that we have to calculate it for 3 hours. Okay, so the DRH is obtained by convolving the IUH. What is convolving? Just multiply the peak discharges that you have derived from this IUH equation at each time scale. T is equal to 1 hour, T is equal to 2 hours, T is equal to 3 hours. Multiply with the rainfall intensity, 5 millimeter per hour. That is all you have to do. For T is equal to 1 hour, 5 into 0.184, 0.92. T is equal to 2, 5 into 0.271. Why 0.271? Because at T is equal to 2 hour, IUH is 0.271 centimeter per hour. At T is equal to 3, IUH is 0.224 centimeter per hour. So basically what is happening is we are just multiplying this IUH, right, at different T. Of course, at every time interval can be 1 hour, time interval can be half an hour also, 2 hours also. Every time interval you have to find this IUH, and after that you have to multiply the rainfall intensity with the peak discharge or peak IUH, and then you will get the peak of DRH. That is all you have to do. Once you get the peak of DRH, you can draw the DRH. As you see, T is equal to 1 hour, it is 5 times the 0.184 because 0.184 is the IUH at T is equal to 1 hour. Right? IUH at T is equal to 1 hour. So that is why I have multiplied 5 with that IUH at 1 hour to get the ordinate of after 1 hour. Then T is equal to 2 hour, I get ordinate of 2 hour. 3 hour, I get the ordinate of 3 hour, and I can easily draw the hydrograph at the outlet. Correct? So it will become 0.92 after first hour. After second hour it is coming 1.355, and after third hour it will starts to reduce because that rainfall was for 2 hours only, so this is another hour. So the hydrograph will just join the point and the flood hydrograph will be drawn. So this is all to it, and you can apply this method for hydrograph routing, even peak discharge insights, timing effects, and of course this all will impact into the flood mitigation measures. So that is all I have to say today. So this is the brief introduction and how you can use Nash's IUH for flood routing. Thank you and hope to see you again. This note will be available in the description. I have given the link for that description. You can download this note from there.